So here's the rule. And it's good for a couple reasons. It keeps reinforcing what the rule is, and it helps you kind of break this down into steps. You can focus on the derivative you're supposed to do at that moment. All right, so how's this come out here? X squared, what happens in here? Now if I simplify this, I can compare it to the derivative of the simplification of this. So let's see, what do we get here? 2x to the what? Now look, remember how subtracting one, I subtract the numerator and the denominator? When I add one, I add the numerator on there. Remember, 7 and 5 is 12. 12 fifths. Plus 7 fifths x to the 10 fifths, 12 fifths, 12 fifths. So I get, what's 2 plus 7 fifths? Because these are like terms, right? Beautiful. Ah. So if I want to check it, what was the simplification of the function in the first place? X to the 17 fifths, right? 10 fifths plus 7 fifths is 17 fifths. Derivative of that would be 17 fifths comes down. 17 minus 5 is 20. All right, yay. So please, suspend your disbelief in this section. Product rule becomes the strongest thing around once it's paired with chain rule. Right now it's a little lame, right? You're like, why wouldn't I just do this? Well, because you're getting used to product rule before it really comes in monster handy. So let's talk about quotient rule. And by that time, we'll see what time it is. I might have to sneak one more thing in. So, again, if we wanted to analyze this, I could look at, let's see, what would this look like? It would be f of x plus h over g of x plus h minus f of x over g of x all over h. I'm going to do the first couple of steps here and try to see if you guys see how it's very similar to what we were doing before. Well, what do you do with this? What's kind of screaming out at you to do a certain thing here? Cancel what? A little bit optimistic. Yeah, what do you have on top? You have two fractions subtracting. So then what do you do? I think I heard somebody say it over here. Yeah, LCD. So we get, what do you have? What is the LCD here? What's this guy missing? He's got
x plus h.
I love you guys. All right, you ready? Do either of these bottoms have an x plus h? No. This has g of x plus h, and this has g of x. So what's he missing that he's got? G of x. What's he missing that he's got? G of x plus h. So we get f of x plus h, g of x over g of x plus h, g of x. I'm going to put minus f of x, g of x plus h, all over h. Now, let me see if you guys can handle this next thing. If you compare the top of this to what we got for the product rule, they're the same. So let's skip a few steps. What's the only difference, though? This is going to be over g times g, right? Because we're going to let h go to 0 eventually. there's also one little difference that comes out. Let me try to get you guys to understand why this works. So here's what, if you follow this through, you eventually get to this point. Just be really clear. So the big difference between product rule and quotient rule is there's a minus here, and then of course the g squared, but hopefully everybody sees where that came from. There is a stupid, well, be careful. There's a song for this. My song is top first, because when you take the derivative of first, the top. Why does it make sense that the thing on the bottom is when I take its derivative, it's got a minus in it? So for example, what's the derivative of 1 over x? Yes, so if something's on the bottom, isn't its derivative going to be negative? Because it's to a negative power. So the term that involves g prime is the one that is negative because it's on the flippin' bottom. You don't need a whole big song to remember where everything goes. Top first. Because when I take the derivative of the bottom, it's going to have to be the minus because it was on the flippin' bottom. That's straightforward. That's simple. You're all like, I don't really know what the word simple means, but it's really nice that the product and quotient rule are very similar, but at the same time it's evil. Product rule has a plus, quotient rule has a minus. But product and quotient are opposites, so that should be expected also. So let's try a specific example. What you got, Jeff? So let's try this together. This is especially important. With quotient rule, there's a lot kind of going on. You want to write the rule and then do shit. You don't want to try to do the rule and shit at the same time. The rule is what? What's the sum? First. Okay. So the top derivative times the bottom minus. The top gets to stay the same and the bottom gets a term. So everybody gets a term divided by x minus 5 squared. Just square whatever function was on the bottom. And now you simplify. Now you do your derivatives. What's the derivative of x squared plus 1? 2x. Minus x squared plus 1 times 1. You gas all over x minus 5 squared. Now, let me rewrite this up here. There are certain things that make me cry. When I give stuff back to you, you might see little tear stains. This makes me cry. Square roots don't go across subtraction. Square roots are based on multiplication. They can't distribute across subtraction. This makes a lot of problems easy. Very easy to get to the wrong answer. Don't waste any time losing points. Don't do that shit. And the other thing is, this is a mistake. What I'm about to do. Yay! Right, this is magic shit. That's math at Hogwarts or something. That's crap. What's being divided by 2x minus 5? This and this. So I don't do that shit. What do? You simplify the top and then see if something cancels. I said, don't do this. Please, dear God. That should have been beaten out of your system before you got to me. So let's see. If I distribute that 2x through, and then what happens here? So distribute the 2x through. What happens here? Minus x squared minus 1 all over x minus 5 squared. So I end up with x squared minus 10x minus 1. Can I reduce this? The only way I could reduce it is if the top had a factor of x minus 5 and I factor the top. Can I factor the top? You need factors of 1 that add to be negative 10. If you manage to do that, show me. Right? Now, of course, there are, but they're not whole numbers, are they? Oh, shit. So there ain't no way x minus 5 is going to be a factor of this. So you stop. And then I could ask you the same questions. Find the tangent line to this function at this point. What do? You plug the x value in, you get the slope, you keep going. I mean, every time we learn a new rule, that question is going to pop up again. And that question never changes. Find a slope, get the point, plug it in, you're done. We just keep learning new slope rules, right? New derivative rules. Pretty good. So here, you guys try this.
So is G still at the bottom?
Oh, all right. So be careful. When we did the discussion of how the rule works, this is a function that is actually a ratio of two functions, right? So what could I call the function I'm talking about? Anything I want to. So here, g of x is a ratio of two functions. That's why I refer to them as top and bottom instead of f and g. That could be freaking g. So there's a rule that doesn't give a shit what this guy's called. It just gets applied the same way every time. Good question though, right? You guys done? One second. What's that? Oh, really? Oh, good. I'm waiting. I did that with a teacher who said basically all the time. A new record?
Yeah.
Aw. Fantastic. It's nice to be known for something. I always used to say, if I offend you, just wait a few minutes, I'll probably do it again. I had somebody get offended. It's like, you're in college. Get over that shit. Please don't square the bottom. Because your next step is going to be, does it reduce or something? There's no point to square that bottom. Oh my God, it's just busy work. me catch up to you. So to write the rule out, what would I put here? What gets derivative first? Yeah, the top. And then the bottom just stays the same, sitting there waiting. Minus, leave the top alone, and the bottom gets his term. So you're going to see that idea about parts of a function I'm taking a derivative of getting a term. That idea kind of continues through a few of these rules. So now I get, what's the derivative of this? 1. So I just get this guy minus this times, what is that squared, Jeff? Jeez. 2x minus 3, is that cool? All over. Now, of course, you just have to FOIL this out. You've got to be careful, there's a negative, right? So we're going to get x squared minus 3x plus 1 minus, we FOIL this out, and 14 and 3 is 17. Is that cool so far? Then you distribute the negatives. That minus sign in the middle is going to be the nemesis for a few of you guys. But, x squared minus 3x plus 1 minus 2x squared plus 17x minus 21 all over. No. Right? Stop. Get your like terms together. Negative x squared plus 14x minus 20. Now here, even if the top factors, why would you not care? Because there ain't no way it's going to have this as a factor. So screw it. Don't even look. Just move to it. Now, when would you want to factor the top if it was factorable? If the question is, where are the horizontal asymptotes? Horizontal tangent lines. When would a horizontal tangent line occur for this? What would I have to figure out? When the top is 0. I love it. The only way the derivative is 0 is if the top is 0. And then I'll be curious about if it factors or not. Okay, maybe. Okay. All right. So last thing for today. We're about to get into the last idea. And this is an idea I kind of skipped over for a minute from section 3.1. Because it is a little bit freaky. Again, I know some of you guys know this. All right, just shut up. If I have f of x equals b to the x. Now, we're only going to look at a specific piece of this. We're not going to develop the rule for this yet. So we already have a rule for x to the n. Now we have a rule for ratios of functions and products of functions. This is a whole different class of function, right? This is where the variable is in the exponent. So it's got its own rule. We're not going to fully develop that rule at the moment. We're going to get a really nifty place where this number comes out. So can you guys set up the limit definition to find this guy's derivative? Just set that up. So what do you get? What do you hear? I love it. Now, for some reason, everybody forgets rules of exponents on something like this. I can rewrite b to the x plus h in a much more useful form. Since I'm adding the exponents, what must I have been doing to the bases? When do you add exponents? When you multiply. So this is b to the x times b to the h. I always get somebody going, where'd you get that other b? No. There are x b's and there are h b's. There. I didn't get any more b's. Create b's, that would be good. Very strange power. Now that I've written all like that, what kind of jumps out at you? What can I do to the top? And something interesting is that factor that b to the x doesn't give a shit about h. No, so I can write it out here. B to the x times, the limit is h goes to 0, b to the h minus 1 over h. So this guy is everything, right? Whatever that limit is, I then would know the answer. So what's really interesting is, do you see how for a function b to the x, the derivative has b to the x in it times some number. That is neat. This is a number, right? This is going to be a number. Because what's b? Hopefully everybody's cool with the fact. What's b? B is a number. It's not a variable, right? It's a constant. So this is 2 to the x, 8 to the x, whatever. So this is just a number. So this is a derivative. It's almost its own derivative. It would be its own derivative if this limit was. When would this equal this if this piece was 1? Yeah, I like it. I love some of you guys are like, I'm not going to say it out loud. I'm going to motion to you like, take the base, slide. All right. So, what's really neat, let's investigate a couple things. Let's review some old style stuff. Do this for me. Some of you guys, how about all the guys do this? Make a table of values for this. And all the girls do this one. All right? All the men make a table of values for investigating this guy. And all the girls make a table of values for the 3 option. Just because. Here. Right. Okay. Oh shit, I lost that. All right. So you guys gonna help with that. All right. Men, what did you get for, let's see, this one. Anybody do that one yet? Zero something one. Point. Yes. 7. 7 who?
7, 6, 8.
Thank you. Something like that. Loud. All right. What about when I step 10 times closer? Yeah. 0.695. Right. And then this is going to be 0.6933. You get the same stuff for negatives. Or maybe not. I can't remember now. Do you? I'm curious though. Let's see. Negative 0.1. 0.67. I mean, for this one you get 0.67. But if you step in, negative 0.01. There, bum, bum, bum. Here you get 0.69. So they are approaching 0.69 basically for both sides. All right. Women, what did you guys get here? Anybody do that yet? Say again. 1.161. Okay, sounds right. 1.1 say blah blah. What about when you step one step closer? 1.10. 1.10? And here basically the same thing, right? Remember correct? Or what'd you get?
Yeah.
Yeah, okay. And we go from the other side, it will also approach 1.10. The important thing is, remember, what was it? Wouldn't it be interesting to find a function that is its own derivative? Would that not be, like, even the slightest bit interesting? Right? A function whose derivative is itself, which really means the function tells me its own slope as I'm drawing it. Okay, that's weird. So which one of these is closer to 1, which would mean the function that would be its own derivative? Well, the 3 is. There's a special number right in between 2 and 3, which ends up being the exact number that makes this come out to be 1, and that number is e. 2.72, whatever. Right? So e is the number such that it is its own derivative. Why does that make sense if I look at the graph of e? What does e look like? Somebody just do it in the air for me real quick. What's e to the x look like? Yes, cool. Swoosh. And so back here, what is the slope approaching? The slope is becoming very flat, so the slope is approaching 0. Isn't the function also approaching 0? What's happening here to the slope? It's getting, what's happening to the slope? It's getting larger, and so is the frickin' function. Right? So e is the only function who is its own derivative. E kicks so much ass. Yeah, like give me some derivative of e stuff. Yes?
Does that work like the second and third derivative, right?
Totally.
It does.
Because if f of x is e to the x, if f prime is e to the x, f double prime would just say take a derivative of this. Well, that's still e to the x. F 18 billion primes of x would be e to the x. It's crazy. Crazy sauce. I don't know, real quick, while I'm thinking about it, do you guys know another place where e comes from? If I graph 1 over x, don't worry about this side. I go from 1, and I say, now of course, pretty much only math geeks would sit there and do this, but that's where math came from, a bunch of math geeks sitting there doing shit. How far up would I have to go until the area of this is 1? What number would that be until the area of this is 1? Well, that number, remarkably enough, is e. The area under this function is 1 if I go from 1 to e. And you're like, why the hell would you want to know that shit? Well, there's some reasons. But to me, that's a very interesting place where e kind of pops out from. Later this semester, we'll be able to prove that really easily once we learn antiderivatives and stuff, because that's what antiderivatives do, is find area on your functions. Okay, I think that's almost everything I wanted to do. I think that's enough. I think I've fried your brains enough. Section 3.3, we're going to get into derivatives of trigonometric functions. We already talked about sine before. So we're going to fill in all the blanks for all the other trig functions in section 3.3. Okay.